Hi, hello students. Good evening, everyone. Okay, I hope all are doing well. Anyway, warm welcome all of you to the Infinity Learn JEE YouTube channel. This is me, Surya, your chemistry faculty from Infinity Learn. Hi, Anish. Good evening. Okay, finally, we are moving to our last part of the chemical bonding chapter, that is the hydrogen bonding. I hope you guys have revised all the topics we have covered in the previous sessions. Today, we are going to the last part, that is the hydrogen bonding. Okay, what do you mean by an hydrogen bonding? Something related to hydrogen, right? Yes, it is the electrostatic force. Okay, it is the electrostatic force that exists between partially positively charged hydrogen atom of a molecule and a highly electronegative atom of the same molecule or a different molecule, which means that a hydrogen atom will be present there. Along with that, an electronegative element is also present there. In between a covalent bond, the type of attraction or chemical bond is known as the hydrogen bonding, right? For example, if I am taking any of the bond like this, okay, this will be our hydrogen and it is covalently bonded to any of the electronegative atom, let's say X. So I can say that these electronegative elements such as fluorine, oxygen and nitrogen, right? Fluorine, oxygen and nitrogen. This hydrogen is bonded to highly electronegative atom. So if I am taking one more molecule just like this, here, right? I am taking one more molecule of HX. What will happen here? We know that X is having high electronegativity, right? So X is highly electronegative, right? So which means that these electron pairs are highly attracted by the X minus. So it is acquiring a partial negative charge, right? So I can say this as delta minus. So due to the presence of these electronegative atom, hydrogen will acquire a plus positive, delta positive charge, right? So there is a difference between these electronegativity. There will be a partial bond characteristic existing between the electronegative atom of one molecule to the hydrogen atom of another molecule. Are you getting the point? So the dotted lines represented by the hydrogen bond, which means that whenever two molecules containing hydrogen atom and an electronegative atom bonded together, due to the electronegativity difference between these atoms, there will be existing a chemical bond of attraction or a force of attraction between the highly electronegative atom as well as the hydrogen atom. That type of bond is known as the hydrogen bond. Clear? Yes, fine. Now, depending upon the molecules, whenever this hydrogen bond is existing between same molecule or different molecule, we can divide this hydrogen bonding into two types that are, first one is the intermolecular hydrogen bonding. Okay, first one is the intermolecular hydrogen bonding and the second one, it is the intramolecular hydrogen bonding. Intramolecular hydrogen bonding. Let us see one by one. First one is the intermolecular hydrogen bonding. Then, whenever any molecule which is given in the solid state or gaseous state, we can say that the magnitude of hydrogen bonding is maximum in its solid state. Right? This is an important point to be noted. Clear? Now, the first category of hydrogen bonding, that is the intermolecular hydrogen bonding. As the name, it suggests that it is between the molecules, right? Whenever two molecules are combined together, we can say that the hydrogen bonding that is existing between the molecules. So, a hydrogen bond that is formed between a partially positive hydrogen atom And an electronegative atom of different molecules. Different molecules is known as the intermolecular hydrogen bonding. Intermolecular hydrogen bonding, right? So we can say that this bond is existing between the molecules. Then what are the examples? The first one example I have taken here, it is hydrogen fluoride, which means hydrogen is bonded to fluorine atom, right? Hydrogen is bonded to fluorine atom. So this will be our hydrogen and it is covalently bonded to fluorine atom. Now if I am taking another molecule of HF, right? Another molecule of HF. Okay, due to the electronegativity difference, fluorine will acquires a minus delta negative charge. Here it is delta positive. Here it is delta positive and it is delta negative, right? So a bond is existing between these fluorine and hydrogen atom, right? Similarly, if I am taking one more bond here also, you can see that covalent bond is forming, right? I mean hydrogen bonding is forming here. So we can say that these dotted lines are known as the hydrogen bonding, and this particular hydrogen bond is known as the intermolecular hydrogen bonding. Intermolecular hydrogen bonding because this hydrogen bonding is formed between these 2 or 3 HF molecules, right? 2 or 3 HF molecules. Clear? Now the second example, that is the water molecule, right? In the case of water molecule, it is shown that this will be our water molecule, that oxygen is bonded to hydrogen atom. Oxygen is more electronegative. So due to the presence of 2 lone pairs, right, there will be aqueous 2 delta minus charge here. Here it is delta plus, right? So whenever I am taking few more water molecules, it will forms hydrogen bond here, right, towards one of the water molecule, and here is also it will forms hydrogen bond with another water molecule. Here is also it will form the hydrogen bond, right? These dotted lines are representing the hydrogen bonding here. It is known as the intermolecular hydrogen bonding. Clear? Hi Shubhajit. Now here are some of the examples. That is ammonia molecule, right? Ammonia molecule in which hydrogen atom is bonded to the highly electronegative nitrogen atom. So when we are going here about the electronegativity difference, you will see in that it will accuse delta positive, it will accuse delta negative, right? Due to the difference in electronegativity, one of the hydrogen atom from the first ammonia molecule will bonded to the nitrogen atom of another ammonia molecule, right? So these dotted lines, this is exhibiting the intermolecular hydrogen bonding here. Here is the next example. If we are taking ammonia in water, right? Here, in the case of ammonia molecule, it will accuse delta minus and it is delta positive, right? Then, in the case of water molecule, due to the highly electronegative oxygen atom, hydrogen exhibits delta positive and oxygen exhibits delta minus. So, here it is the intermolecular hydrogen bonding existing between the nitrogen atom of ammonia with one of the hydrogen atom of water molecule. Clear? Here is the another example, that is the formic acid, right? Formic acid. Formic acid means HCOOH, right? HCOOH. So here delta minus and delta plus. Similarly, delta minus, delta plus. So whenever two formic acid molecules are come together, due to the electronegativity difference, there will be the partial positively hydrogen atom that will combine with the partial negative or the highly electronegative oxygen atom to form these hydrogen bonding. Clear? Then another example is the parafluorophenol. This is the para position, right? Opposite position. OH molecule means benzene ring with OH molecule is known as the phenol molecule. To the para position, it is having fluorine group, so it is called a parafluorophenol. Again, whenever two parafluorophenol molecules are come together, there will exist a intermolecular hydrogen bonding between them. Next example, it is the metanitrophenol. 1, 2, 3, right? 1, 3 position is known as the meta position. I hope you have aware about these position, ortho, meta, para positions. Here in the first phase, it is OH molecule, therefore it is phenol. In the third position, it is having nitro molecule, so it is named as metanitrophenol. Whenever two metanitrophenol compounds are come together, there will existing hydrogen bonding, that is the intermolecular hydrogen bonding between these molecules. The last example, it is the parahydroxybenzaldehyde. Parahydroxybenzaldehyde. Right? This is the aldehyde group, then OH group, parahydroxybenzaldehyde. Whenever these molecules come together, again the hydrogen bonding is existing, that is known as the intermolecular hydrogen bonding. Are you getting the point? Is it clear? Yes, fine. Now let me move to the second type of hydrogen bonding, that is the intramolecular hydrogen bonding. What will be the difference as compared to intermolecular? Intra means within the molecule, right? Intra, within the molecule. Which means within the same molecule, within the molecule. So we can define it as the hydrogen bond formed between partially positive hydrogen atom and the electronegative atom present in the same molecule of the substance. Same molecule of the substance is known as the intramolecular hydrogen bonding. Let us see the examples. The first one is the salicylaldehyde, otherwise it is also named as orthohydroxybenzaldehyde. This is the hydroxy group, then this is the aldehyde group, right? 1, 2 position, that is the orthohydroxybenzaldehyde, otherwise it is named as salicylaldehyde. So as you can see here, this is a delta minus, right? This is delta positive. So again, due to the presence of C or CHO, right? Here it is delta minus, it is delta plus. So within the molecule, otherwise same molecule existing the hydrogen bonding between the electronegative atom. So this dotted line is representing the intramolecular hydrogen bonding. Okay, the another example is orthonitrophenol. Ortho position, right? OH means phenol group. In the ortho position, it is having nitro group, right? Yes, it is. This is the group NO2, right? OH and NO2. So orthonitrophenol, again delta plus, delta minus existing within the molecule. So experiencing the intramolecular hydrogen bonding. Few more examples are there. The next one, it is the orthofluorophenol. Ortho position, it is phenol, right? OH group, then fluorine group, delta minus, delta plus. So existing the intramolecular hydrogen bonding. Then the next one, orthonitroaniline. Orthonitroaniline. This is NH2, right? This is NH2. So, delta minus and delta plus. Electronegativity difference. So, existing intramolecular hydrogen bonding between the molecules. Similarly, this is a salicylic acid, which means ortho-hydroxy-benzoic acid. COH group, right? It is the acid group. OH means hydroxy. So, here delta plus, delta minus, forming intramolecular hydrogen bonding. Clear? Okay, these are all about the hydrogen bonding. That is the classification of hydrogen bonding. Inter means it is the between the molecules, right? The hydrogen bond that is formed between the molecules is known as the intermolecular hydrogen bonding. Whenever we are discussing about the intramolecular hydrogen bonding, it means that the hydrogen bond that exists within the same molecule, right? Clear? Now let us discuss about what are the effects of hydrogen bonding or the consequences of hydrogen bonding. The first one, it is about the solubility, right? Solubility of molecules due to the presence of hydrogen bonding. So I can say that whenever any molecule which is presently is having intermolecular hydrogen bonding between the molecule, right? So solubility will be higher, which means that solubility is directly proportional to the intermolecular hydrogen bonding. Then just opposite, it will be directly proportional to 1 by intramolecular, otherwise it is inversely proportional to the intramolecular hydrogen bonding. What do you mean by that? Inversely proportional? If any molecule that contain intramolecular hydrogen bonding, its solubility will be decreasing. Clear? Okay, here is some example. For example, if I am taking CH3OH, methanol, right? CH3OH, methanol, or C2H5OH, that is ethanol, in water. Whenever it is introducing into the water, there will be existing the intermolecular hydrogen bonding between the hydrogen atom and the electronegative oxygen, right? So, due to the presence of that intermolecular hydrogen bonding, it will experience more solubility in water. Clear? Here is the next example, that is if I am taking orthohydroxybenzaldehyde and para-hydroxybenzaldehyde in the water, right? What will happen to the solubility? Or I can say that if I am taking orthohydroxybenzaldehyde in water, it is shown that it is less soluble in water as compared to the para-hydroxybenzaldehyde. Can anyone please give me the answer? What will be the reason behind that as according to the hydrogen bonding? Just compare the structure of molecules, then checking that whether it is having intermolecular or intramolecular hydrogen bonding, then connect with the solubility. Yeah, Anish, you can say. If I am taking the orthohydroxybenzaldehyde, which bond is presenting, whether it is intermolecular or intramolecular? Okay, these are the structures of orthohydroxy and para-hydroxybenzaldehyde. Orthohydroxy and para-hydroxybenzaldehyde. While checking the structure itself, you can identify that there will be the existence of hydrogen bonding, right? There will be the existence of hydrogen bonding. So we can say that in the case of orthohydroxybenzaldehyde, there will be the intramolecular hydrogen bonding, right? Intramolecular hydrogen bonding within the same molecule. So we can say that whenever the molecule containing intramolecular hydrogen bonding, its solubility decreases. That is why orthohydroxybenzaldehyde leaves become less soluble in water because of the intramolecular hydrogen bonding. Clear? Next property, it is the boiling point, right? How boiling point of the molecules are relating to intermolecular as well as intramolecular hydrogen bonding. The same model like this. Boiling point is directly proportional to the intermolecular hydrogen bonding and it is inversely proportional to the intramolecular hydrogen bonding. Okay. So we can say that the melting as well as boiling point, also melting point also affects like this. So the melting point and boiling point of water, ammonia and hydrogen fluoride, etc. are found to be highly expected, abnormally higher than expected, What is the reason behind that? If you are taking water, ammonia or hydrogen fluoride molecule. Hydrogen bonding, right? In the case of water molecule or ammonia or hydrogen fluoride, there is the presence of intermolecular hydrogen bonding. As the intermolecular hydrogen bonding increases or the presence is there, we can say that boiling point or melting point also increases. That is the reason behind that, due to the presence of intermolecular hydrogen bonding. Then, if you are taking water and hydrogen fluoride as a specific case, right? Then we can say that water has higher boiling point than the hydrogen fluoride. Water has higher boiling point than the hydrogen fluoride. Hydrogen fluoride is forming the intermolecular hydrogen bonding, right? So if you are considering one of the hydrogen fluoride molecule, what is the possibility of forming hydrogen bonding there, or how many hydrogen bonding is formed for a single hydrogen fluoride atom? Is my question is clear? So if I am taking a hydrogen fluoride molecule for the intermolecular hydrogen bonding, how many bonds are forming? How many hydrogen bonds are forming for a single HF molecule? These dotted lines represent the hydrogen bonding, right? Okay, this is the one hydrogen bond, this is the another one, right? Second one. So we can say that whenever we are taking the hydrogen fluoride molecule, it has the tendency to form two intermolecular hydrogen bonding at a time. Now, if I am taking the water molecule, right? Water molecule. I can say that two lone pairs are present on the water molecule. So there is the possibility of forming one of the hydrogen bond here, then here it is also a possibility, right? Which means that at a time water has a tendency to form four intermolecular hydrogen bond between the molecules. So where is the maximum? where is the maximum hydrogen bond is forming, whether it is in the hydrogen fluoride or water molecule. Water molecule, right? Because water molecule forming 4 hydrogen bonding in between the molecule. That is why water has high boiling point as compared to the hydrogen fluoride. As compared to the hydrogen fluoride, because stronger hydrogen bonds are exist. Okay, because large number of hydrogen bonds are in the water as compared to the HF molecule. Clear? Now, if I am taking the hydrates of halogen groups, right? Fluorine, iodine, bromine and chlorine, what will happen to the boiling point order, right? For example, if I am taking HF, right? Okay, in general, whenever we are moving down the group from as the size increases, right? So which means that boiling point also increases. So we are expecting the order of HF greater, right? HF greater, HCl. Increasing order, right? So HF, HCl, HBr and HI, right? This will be the expected order, but in the case of HF molecule, due to the presence of intermolecular hydrogen bonding, its boiling point become more, right? It has a maximum boiling point. So we are getting the order of HF greater than, HI greater than, HBr and HCl. Clear? Due to the presence of intermolecular hydrogen bonding in the case of HF, it will experience more boiling point as compared to the other elements, right? HI, HBr and HCl. Now, what about the second one? Here it is the oxygen group members, right? Oxygen, sulfur, selenium and tellurium. Similarly, whenever we are moving down the group, oxygen, sulfur, selenium and tellurium, the hydrates of the oxygen, sulfur and selenium, it will increases, boiling point increases, which means that we will expecting the order, expected order it is okay, this will be the expected order of boiling point of these groups. But whenever we are taking the intermolecular hydrogen bonding concept, we can say that in the case of water molecule, there will be the presence of intermolecular hydrogen bonding. That is why it is having maximum boiling point as we are expected, as against we are expected, right? So this will be the correct order. Clear? Then the last property, it is the viscosity property, right? Viscosity, as you already know, it is the tendency to flow, right? It is the property of fluids or liquids. So we can say that similarly, viscosity is also directly proportional to the viscosity is also directly proportional to the intermolecular hydrogen bonding, right? Intermolecular hydrogen bonding, which means that whenever the molecule is having intermolecular hydrogen bonding, it will experience the higher viscosity because there will be a strong force of attraction, right? whenever there is having intermolecular hydrogen bonding, there will be a strong force of attraction. So it is very difficult to flow the liquid, right? Which means its viscosity increases. So in the case of this particular molecule, first one is water, then methanol, then acetone, right? CH3 or CH3 acetone molecule. So due to the presence of intermolecular hydrogen bonding in the case of water molecule, it is more viscous as compared to all others. Clear? Okay, these are all about the hydrogen bonding. So far we discussed about what is hydrogen bonding, right? It is the electrostatic force of attraction between the hydrogen and the electronegative atom. Two types of hydrogen bondings are present: inter and intramolecular hydrogen bonding. Then they are how they are affecting the boiling point, viscosity, and the melting point and solubility of the molecules, right? So now let us practice some questions. Okay, here is the first question. Select the compound from the following that will show intramolecular hydrogen bonding. Intramolecular hydrogen bonding. Options are given here. The first one, it is ethanol, then water, ammonia, and orthonitrophenol. Yes, Farhan, option D. What about others? Is there any other options? Yes, Farhan, you are right. Orthonitrophenol is the correct answer. And each question is here which one having intramolecular hydrogen bonding, not about intermolecular hydrogen bonding, right? Intramolecular means within the molecule, right? So we are taking the example here. This is the orthonitrophenol. There will be the hydrogen bondings existing between hydrogen and the nitrogen atom of the same molecule. Nitro group and the hydroxy group, right? So option D will be the correct answer. Clear? Now we are going to practice some questions which we have already covered in our previous sessions. That's the subtopics we have covered. Okay, this is about the hybridization part. I hope you guys have watched the recorded session for the hybridization video. If not, just watch the session after completing this class. Then, the number of species from the following in which the central atom uses sp3 hybridized orbitals in its bonding. Some of the molecules are given here. First, you have to find out the molecules which are having sp3 hybridization. Okay, Farhan, option B, right? Then, which are the three molecules? Yes, NH3, H2 and CH4, right? Yeah, right. Yes, option B is the correct answer. NH3, CH4 and H2O, right? NH3, CH4 and H2O. Then, give me the idea about how you are calculating the hybridization, or how you are checking the hybridization of the particular molecule. Is there any concept is behind that? Okay, if you are familiar with the molecules, then it is fine. Otherwise, if you are not familiar with the molecules, then you have to find out the hybridization. There will be one formula to calculate the steric number. Actually, steric number is a number which is equal to the number of sigma bonds plus number of lone pairs present on the central atom, right? Otherwise, whenever we are having any of the charged species, we can calculate the steric number using this formula also, right? Half into the number of valence electrons on the central metal atom plus number of monovalent atom. Monovalent means the atoms that is having valency of 1. Monovalent atom. Then plus or minus charge, which means that whenever you are having any anion, right, negative charge. So we are adding here plus or minus charge. Okay, if it is having the anionic charge, you will just add that. If it is having the cationic charge, you will just minus that. Clear? Yes. Yes, Farhan, you are correct. It is the single bond atom bonded with the central atom and the valence electron in the central metal atom. That will be known as the steric number of the particular molecule. While knowing the number, we can predict the hybridization, right? So similarly, if you are calculating this here, I am taking the 3 examples only here, NH3, right? What will be the steric number here? Half into number of valence electrons on the central atom. Central atom, it is nitrogen, right? So it is having 5 plus number of monovalent atom. Hydrogen is the monovalent atom, so it is having 3 hydrogen atom. So adding here 5 plus 3, 8 by 2, that is equal to 4. 4 means it is sp3 hybridization, right? 4 means it is sp3 hybridization. Then what about the next molecule, water molecule, right? H2O. Steric number is equal to half into central atom is oxygen, right? Central atom is oxygen here. The number of valence electrons in the oxygen atom is 6. 2, 6, right? 2, 6 is the electronic configuration, so 6 is the valence electrons. 6 plus 2 hydrogen atom is surrounding, monovalent atom. 2, 6 plus 2, 8 by 2, again 4, sp3 hybridization. And the last one, CH4, right? Carbon will be the central atom. So calculating the steric number, that is equal to half into, carbon is having 4 valency, right? 4 valence electrons. 4 plus, it is surrounding 4 hydrogen atom, that is 4 monovalent atom. 4 plus 4, 8 by 2, that is equal to 4 again, which means these 3 molecules exhibiting sp3 hybridization. That is option B will be the correct answer. Clear? Okay, now here is the third question, that is the few diatomic molecules are given here. Find out the bond energy which is maximum in this molecule. Hi Pintu Kumar and Karthik. Okay, what is the answer here? N2, right? Yes, option 2, that is N2 is the correct answer. In order to find the bond energy, you have to find out the bond order, right? Bond order is directly proportional to the bond energy. So you must be calculating the bond orders here. You will get bond order of fluorine is equal to 1, the nitrogen it is equal to 3, oxygen it is equal to 2, bromine again it is equal to 1, right? So which one is having the maximum bond order? For nitrogen, so it is having the maximum bond enthalpy. Okay, fine. Clear? Karthik, I am from Kerala. Okay, there is one more trick you have to be memorized to calculate the bond order without doing the molecular electronic configuration. For example, if I am taking here this will be our number of electrons, right? Total number of electrons. Then its bond order will be 3, right? Now you are taking here 13, 12, 11, 10. You must be remember that for 14 electron system, bond order will be 3. Then, in order to find out the other number of electrons, you will just decreasing 0.5 each cases, right? So, here it will be 2.5. Then, what about here? 16 electron condition, bond order 2, right? Take the difference between 0.5. 2 minus 0.5 again 1.5. Then it is 1, 0.5, 0. Similarly, for 13 electron also, it will like going like this 2.5, 2, 1.5, 1, 0.5, and for 8 electron system, it will be 0. 8 electron system, it will be 0. These are the bond orders and these are the total number of electrons present in the diatomic molecule, right? Take this as the reference. Then while moving down and going up, take the difference of 0.5. Clear? Now here is the next question. The bond order of acetylide ion as same as that of which of these following ions? First you have to identify which one is the acetylide ion, then find out the total number of electrons in the acetylide ion, then what about bond order, then checking which one have the same number of electrons or the same number of bonds formed between the atoms. Farhan, are you sure? It is option D. Karthik, I am graduated from the NIT Calicut, postgraduated. Okay, option C will be the correct answer. So we are taking here acetylide ion, right? CH triple bond, CH is the acetylene molecule. If it is acetylide ion means it is having negative charge. Then what will be the total number of electrons here? Total number of electrons. Two carbon, right? 6 plus 6, 12, plus 1 hydrogen atom, 13. Minus charge means adding 1 electron. In total of 14 electrons, right? In total of 14 electrons. Yes. So, we have an idea about the bond order, right? No need to write the molecular electronic configuration. For 14 electrons, what will be the bond order? For 14 electrons, what will be the bond order? Electron 3, right? Bond order will be 3, which means that this molecule also have the bond order of 3. Then, in these options, you have to calculate the total number of electrons, which means that all the isoelectronic species have the same bond order, right? So, if any of the molecule is having 14 electrons, it means that it will be the isoelectronic species having the same bond order of 3, right? Now, for what about the total number of electrons in the case of first molecule? N2 plus. For one nitrogen atom it is 7, right? Okay, for acetaldehyde ion, that is CH, okay, acetaldehyde ion, we will get the answer of 1.5. But it is acetylide ion, right? Acetylide ion means CH triple bond C minus, then it will have the bond order of 3. Clear? Got it right, Farhan? Nitrogen, right? 2 nitrogen, it is 7 plus 7, 14 minus 1, that is equal to 13 electron. Then what about O2 plus? O2 plus means 8 plus 8, 16 minus 1, that is equal to 15 electron. For nitrogen, NO plus ion, right? Nitrosonium ion. Nitrogen is having 7 electrons, oxygen is having 8 electrons. 8 plus 7 minus 1, that is equal to 14 electron. Then O2 minus means 8 plus 8, 16 plus 1, that is equal to 17 electron. So we have to identify the species having 14 electron, that is option C, NO plus. Clear? Here is the next question, and this was already given as an homework in the yesterday's class. I hope everyone tried this and got the answer. Okay, what will be the answer here? Species is given here, B2 plus species. Find out the number of unpaired electrons present in the particular species, then spin-only magnetic moment. Read the question carefully, some mistakes will happen. It is given that the spin-only magnetic moment value of B2 plus species is dash into 10 to the power minus 2, which means that this will not be a decimal point, right? B2 plus, right? How many electrons are there? B2 plus 1 boron 5, 2 boron 10, right? 10 minus 1, that is equal to 9 electrons. Write down the electronic configuration. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2. Then for 9 electron system, which will be the next orbital? Right, this will be the electronic configuration of B2 plus species. It is having one unpaired electron, so we can calculate the spin-only magnetic moment. Mu is equal to square root of n into n plus 2, where n is the number of unpaired electrons, right? Here it is having unpaired electron, only one unpaired electron, so we are taking here square root of 1 into 1 plus 2, which means that is equal to root 3, right? So for the easiness of the question, it is given that root 3 is equal to 1.73. So that is equal to 1.73. But our question is that what is the value? Value is given it is as dash into 10 to the power minus 2. So we can take it as 173 into 10 to the power minus 2. Which means option C will be the correct answer. Clear? Okay, here is the next question, which is based on the VSEPR theory. We have already discussed, right? VSEPR theory. This is an assertion reason type question. An assertion is given as the HOH bond angle in water molecule is 104.5 degree, and the reason is given that the lone pair repulsion of electrons is higher than the bond pair repulsion. You just have to identify whether these assertion and reason are correct or whether it is the correct explanation or not. Option D, right? Yes, Siddharth, you are correct. No, option B, right? Okay, this was a mistake from my side. Option D is the correct. Okay, the HOH bond angle in water molecule is 104.5, right? This will be our water molecule. Actually, according to the sp3 hybridization, we will expect the structure or the geometry of molecule as tetrahedral, right? Tetrahedral of bond angle 109 degree 5 minute. But due to the presence of these two lone pair electrons, it will experience a shape of bend shape having bond angle of bend shape having bond angle of 104.5 degree. What is the reason behind that? Because of this lone pair repulsion. The lone pair repulsion is more as compared to the bond pair repulsion, right? Fine. Okay, here is the last question. This question is based on the calculation of dipole moment. Few molecules are given here. You have to identify the total number of molecules with zero dipole moment. Four or three? What is the confusion there? Whether it is 4 or 3? Siddharth? First you have to identify whether how much of the molecules are having the symmetrical structure, right? Whether which is having symmetrical structure, their dipole moment can cancel each other, which means they have the dipole moment of 0. So I am taking here CH4, then BF3, right? How we can represent the dipole moment? Okay, these dipole moments are equal and opposite, so it will get the 0 dipole moment here. Again, here it is also represented here like this because fluorine is more electronegative. Equal and opposite, getting mu is equal to dipole moment is equal to 0. What about here also? Again, equal and opposite having the dipole moment of 0. Dipole moment is equal to 0. Which molecule? HF, right? Okay. How we can predict the dipole moment here? Which atom is electronegative? How we can write the dipole moment like this? Fluorine is having more electronegative, right? So hydrogen having the less electronegativity. So fluorine is attracting the more electron pairs towards this. So this will be the dipole moment is towards the fluorine atom. That which means that there is no any zero dipole moment. It experiences some dipole moment in the Debye order, right? Clear? Then you can calculate in the case of water molecule is also there. 2 lone pairs are there. Then what about other? Ammonia is also there. Due to the presence of lone pair, there will be maximum dipole moment as compared to the normal ammonia structure, right? Clear? Okay, that's all from my side for today. Again, the reminder about the AITS, all day test series for the JEE Main Session 2 and JEE Advanced 2025. Just enroll fast. You will get a discount of 2,999 using this YouTube 50 off code. So don't miss it. So far we have successfully completed our chemical bonding and molecular chapter. We have started from the starting of chemical bonding, right? We have studied about the ionic bonding, covalent bonding. Then we have studied about more theories. First one starting with the Lewis structure, right? How to draw the Lewis structures, how to calculate the formal charge and so on. Then we studied about the octet rule. Finally, we are moving to the bond parameters, right? Bond length, bond energy, bond order, and what else? Bond length, right? Bond order, bond energy. Like that. Then finally, we move to the VBT, valence bond theory, VSEPR theory, and the extension of VBT, that is the molecular orbital theory and hybridization. So we have just completed the chemical bonding and molecular structure chapter. I hope everyone get the correct. I hope I have completed all the important topics from this chapter. Next, on Monday, I will be coming back with the new chapter, that is thermodynamics. So far, thank you so much all of you. Then don't forget to subscribe our channel. Do like, share this particular session to your friends and family also. Till then, bye-bye. Thank you.